Hi there, this is Amir from Simra-tech, and today I'm going to show you how Simra can design systems. It can use existing IPs, blocks, connect them together, and plan a floor plan of the chip. And for the testbed, we're using a SKY130, and I have an elaborate catalog of open source designs. I've cloned all the designs here. They're all the blocks and from organizations, individuals to universities. And I asked Simra to create me a catalog so I can show you what is inside here. We can see uh, in the menu, we have some system on chip harnesses. This is from Efabless. It's a silicon verified tape out ready. We have some SRAMs. We have uh, in, in category of power management, voltage regulator, we have some stuff. We have sensors and precision bias networks. This is from NTNU in Norway. We have also band gap from Stanford. We have some high performance data converters from Linz University, and from also from Alabama. We have also data converter, and you can see it's a quite an elaborate. We have also some RF and frequency synthesis, also from Linz University and Eindhoven. And yeah, so now that we have all of this is actually a 43 pages report. I'm gonna put it down in the comments. You can check it out. It has all the specs, area, and it extracted what the authors included in the files and what would be appropriate for a catalog to include. And yeah, we have it here. And now that we have like a complete set of blocks, and probably some of you in your university organization from your colleagues, you already have also like a really complete IP blocks. But part of the engineer's work is to how to can we connect them together for different applications, different systems, and yeah, let's test it out with Simra. I'm going to use voice mode using Whisper, so I don't need to type this stuff down, and you can also hear what we type here. So we have a bunch of open source designs from the community. You can see the catalog here, and I'm wondering what type of systems can we build that is would be ready to tape out. So it came up with three system category classes, and it mentions that Efabless had a Caravan, which is basically a harness, and it would make it tape out ready for us because it has the pads and EST protection, everything we need for the tape out. And yeah, so the first system is ultra low power biomedical IoT sensing. It could be for ECG, EEG, and I think could be other stuff as well. We have the analog front end from Linz University. It's a very low noise floor. It has a really good SNR and really low power. We have some sensors and references here. It has the oscillator-based temperature sensor, and we have a band gap reference for power and reset. We also have a low dropout voltage, and we also have a power and reset supervisor, and we have also storage processing with the SRAM. So basically we can do some processing on chip. That's pretty good. Second category, it's a high-speed sensor data acquisition and telemetry system on chip. Yeah, we can see all the blocks that it's using, and it's like from different groups that they open source their designs. And we have also autonomously calibrated power and bias management IC. There's another category. And maybe there is other systems that it overlooked and just gave us the top three. But we can elaborate with it and see if it can find out. So looking at this, the ultra low power biomedical IoT sensing, something that can work for humans, that probably can also work for humanoid robots. And the application that I thought maybe we can test is see if we can design a chip for robots to have a really good humanly handshake, with a firm grip. And we can see if we have the blocks to be able to design that. So I was wondering if we can design a system on chip for a robot hand. I want like a humanoid robot hand that has a good humanly handshake, a good grip and firm, but not too firm to break my hand. And can you see if we have all the blocks ready for this? So it comes back. It says, yeah, we have all the silicon proven blocks. We can have a closed loop robotic hand control system on chip. For the grip sensing and safety chain, the analog front end is suggesting the sensor biasing, high resolution digitization with the SAR ADC, ultra fast hardware safety interlock, which we can use the rail-to-rail comparator with the 1 millivolt resolution. And we have the actuator thermal monitor. We have the processing and control unit, can be done with the PicoRV32 RISC-V CPU, and we have 11 direct analog I/O pads. And yeah, we have a wishbone control bus, so system memory, and for actuation and output control, we can have a pulse width modulation with the GPIOs that are existing with the digital pads. Yeah, and we have also a RDAC. We have an 8-bit resistive DAC, which can be used for that. And we have also power and reset, also available from the catalog. So it looks kind of complete. And so the gaps that it found, we need like a transducer element, the physical pressure and force sensors, the piezoresistive skin strain gauge must be off chip. And so we can put that on the PCB maybe. Power bridges, so on-chip IOs cannot drive high current motors directly. External power MOSFETs or H-bridge ICs are required. Yeah, so this is like some stuff that maybe for the first tape out it can be done, like the gaps to be done on the PCB to be able to test it out, and then maybe we find even more open source blocks to be able to complete this. So now that we have this, I want to get down to the specs and the pin-to-pin interface mapping and the block diagram. So now that we have all of this, I want from this application, can we calculate the spec we need for the system so we can drive down to each of the blocks and also have the pin-to-pin interface mapping. And also I like to see a block diagram. How are we going to connect all of this together? All right, so the results are in. First thing I asked was the system and block specifications. It tried to come from the application and see like what are the specifications we need on the block level and system level. So the robotic finger DC motors have a mechanical time constant of 10 milliseconds. So to maintain a stable PID loop without oscillation, the control loop runs at 1 kilohertz. And the force sensing dynamic range is the target peak force is 50 Newton per finger with a touch resolution of 0.1 Newton. So that requires 500 discrete levels. That means like a 9-bit data converter. And we have like the 12-bit, so that's quite, with 64 oversampling, so that's quite sufficient. And on the hardware safety interlock, we have a 1 millisecond latency, so we can see that the continuous comparator can handle that with the 8-bit resistive DAC. Yeah, that's also sufficient. We can see the summary of all the specification. I'm going to create a document with this. You can also review the details. We have the pin-to-pin interface mapping. We have the analog I/O paths. This is from the Caravan of the Efabless. It has like the pad rings already available, and it started to use those for different stuff. So we have four, actually five, for the inputs of the force. So yeah, we have the robot has probably 5 fingers. Yeah, and we have the output here is for the 1.2 volt band gap reference monitor. We have here is an input of from the battery, and yeah, we have LDO regulated here on the outputs. We have another output for 2 times the PTAT for the external tactic sensor, and we have also an output of the resistive deck. And yeah, here you can see there are a bunch of outputs for the motor, pulse width modulation, and yeah, maybe it's easier to see that on the system block diagram. We can see the CPU, there's some processing on chip. We have the all the connections for different blocks. Yeah, you can see it's quite elaborate. It did few reasoning on the generation of this block diagram to make sure it's not misconnecting things. So it's quite elaborate. Like for me even, like I need to think like 100%. Does it make sense? But this is the process. Like with agents, we shouldn't like treat it as like a black box. I give it a prompt, it needs to give me a ready output. We need to have kind of like a conversation. And in this demo, I'm also showing you that I just gonna record my voice and kind of like have a conversation like you're having with a colleague, or for the case of Simra, consider like a junior engineer. Like it gives you something. It's pretty impressive in a very short amount of time that a junior engineer probably gonna take like much longer for giving it to you. But you need to check it out, and it also has capabilities that it learns from you. So the more you work with it, the better it knows your know-hows, and there are a lot of details that these models are never trained on. These details of analog and mixed signal that is like in your mind and it's in your group. So don't expect the agents to replicate that, and be happy that they don't replicate that. This data wasn't available online to get trained on. So yeah, this is how I would suggest to work with the agent. Like you need to have a conversation, you need to verify the outputs. Now that we have this, it's suggesting like as the second to go and generate a template C firmware code for the RISC CPU, for the PID loop and register access sequence to manage this compliant handshake. Uh, maybe that would be more for, yeah, it's kind of for the system verification, but I thought we can go to budget the area, have a floor plan for the chip, and like see what are the steps for getting the verification and simulations going. So yeah, I wanted to see like if we can get the budgeting area we have in the harness available for all the stuff we put in the block diagram. Can you make me a floor plan of the chip so I have like a rough idea of where things are, how much area they're consuming, and yeah, along with what you propose to go for the C-frame code, I want like a plan for the simulation and characterization we need for each of the available blocks, and also the combination of them because it's a closed loop system. So there needs to be verifications also that have a bunch of blocks included together. It can be 2 blocks, it can be multiple blocks. So I want you to think also about that and give me a plan of what would be next steps after we have the floor plan and to be able to start the verifications. Okay, So I'm just pasting the like what I did in conversation, like whisper transcoded. I couldn't. We have actually voice from Simra itself, but I have it in a server that it cannot connect to my microphone. So I'm using something on my laptop to be able to whisper and copy the script. So now we can put this in and we wait till it comes back. All right, so it came back with the request. First thing I asked it was about the area budgeting and the floor plan. It says that in the harness we have approximately 10 square millimeter, and each of the single blocks it included how much area they consume. So you can see this like a half a percentage for the LDO, half percent for the PTAT sensors, 1.7 for the SAR ADC 12-bit. We have the RDAC, it's 0.2% of the area. We have comparator 0.1. We have the thermal guard ring. We have 8% of it for the digital core and 1.5% of it for the SRAM. So just like as a complete of the um, block. I'm not really happy with this diagram. LLMs are still really poor in geometrical generation of stuff, but you can see like around the pad rings, like at least it's not like the location of pad ring how I wanted in a layout, but still it has like the name of each of the signals and which block is connecting, and it tried to bring those blocks close to those pads. And yeah, we can see I also as a list here and the color code of each of them. Well, that's for the pad ring. It also did the C-firmware for the CPU. Um, well, like it needs to be tested, and for LLMs are generally really good at code generation. So but this needs to be tested in a closed loop. So that doesn't really impress me. And yeah, we have the simulation, characterization, and verification plan. It came up with a three-tier verification plan. We have the individual block characterization. It can be done with ngSpice. We have for the SAR, we have for the comparator, and we have for the LDO. And it knows the spec that it needs to get to. So we need to recharacterize, see if we get the same thing. Maybe PDK change, maybe something changed. We saw in one of our previous demos how we can do block characterization. Then it does a subsystem verification, which is some blocks together. You know, we have the power and bias grid. It says to simulating the LDO, the band gap, and PTAT together during power supply ramp up, and brownout to verify correct startup sequencing. We have force acquisition change, injecting ADC capacitor switch transient current into the bandgap reference line to verify reference segment reference stays under 1 LSB, and overforce safety chain where yeah, to not break the bones. And then we have the tier 3 closed loop mixed signal co-simulation. So we need to integrate the RTL for the CPU with Verilog A models of analog blocks. That is electromechanical. So we have the SPICE electromechanical differential equation representing the bridge, DC motor, and piezo resistive skin sensor. Then we have the handshake compliance test for a steady 20 Newton grip, like that's like 2 kilo. I think I would be okay for a pressure of 2 kilo while handshaking. And with transient force overshoot restricted to 10%. So yeah, 2 kilo max. And emergency crash test, yeah, that's important. You can, like, as I said, like these agents don't treat them like they give you, they are not super intelligent. Okay, they can work really well with tools and context you give them, and it did the best job it could. proudly. And from that is like you come in the loop, you verify what it says. And if something doesn't make sense, if 2 kilo doesn't make sense for the hand grip, ask it to find a sensor, ask it to find a reference. There's probably a bunch of references talking about like robot hand design and what is the grip that it needs. If it needs to, I don't know, turn on the dishwasher, then there are some data there. You can just have this conversation with the engine. And everything that we're talking about, like in this folder, you can see that it's generating like the spec, it's generating the spec, it's generating the floor plan, the block diagram, verification plan, and it just keeps updating this thing, and we can keep expanding on this. So, and it comes up like with the next steps. We need to extract post layout CDL PEX netlist. We need to develop a Verilog macro model. We need to compile the C-firm to SRAM, and we need to launch transient subsystem simulations. And yeah, that can go on. Now, uh, I want to just like wrap up what we have so far. I wanted to generate like a system architecture spec document. So and I will put it down into the comments. You can see the same thing. And yeah, I just want to show you like how simple it is. We have bunch of open source blocks on Sky 130, and how in a matter of half an hour we could find bunch of combinations, start planning a system and an application that we could technically take this out like in a matter of, I don't know, days to weeks. Like it needs a lot of verification. Like this gonna take the most of the time, I would say, and also like the layout, the combination of the blocks together, putting it in the floor plan. Um, that's also something I've experimented with Simra, and I like to also show that in the future how we can do some of the automations there. But again, you need to be in the loop. So I want to give you a feeling. You start to treat these agents as some junior engineers that can surprise you sometimes, and then we can start to do more complex things with them. But unless you don't start to get a feeling of how they work and how they treat existing blocks, it's not easy to see how it can help you with your workflows. And we have this catalog. We have it in our sandbox. We are rolling it out. And if you like to play, you can tape out this one. We can help you. You can tape out this chip also with Simra. Like we can help you to automate the whole thing, and maybe in a week or two you can tape it out. So now I talk too much. Let me generate the system architecture document for you. I'm gonna put it down in the comments. And yeah, if you like to see something specific, you can also ask us. We would be really happy. So now I'm just gonna ask it to generate that document. Yeah, so I gonna put this PDF also down in the comments, and we look forward to hear from you.